In today's lesson, we're going to talk about limits at infinity. So in day 5 and in day 3, we looked at limits where x was approaching some number, right? It could have been a fraction, it could have been an integer, but it was always approaching a physical number. Today, we're going to take a look at what happens when my x is approaching infinity or negative infinity. How do we evaluate those types of limits? So what you're going to start off here with is the function f of x equals to 1 over x. This is your parent function for the reciprocal function. And here's what we're going to take a look at. We're going to see what happens when we look at the limit as x approaches infinity for 1 over x, and then as x approaches negative infinity for 1 over x. So here's what I'd like you to do. I want you to take a couple of minutes to fill in the table of values there. I gave you the values of x that I want you to plug into 1 over x. And then I want you to start to notice what the y values are headed towards. And then I want you to come back to the video to take a look if what you have filled in is correct. So if you filled in your y values, this is what you should have gotten. If you plugged in 100, you should have gotten 0.01. If you plugged in 1,000, you would have gotten 0.001. And then if you plugged in 1 million, you would have gotten 0.000001. So as you notice, the x values are getting larger and larger and larger. In other words, we're talking about what happens when my x values approach positive infinity for my function 1 over x. So if my x values were to get extremely large, say 1 billion or 2 billion, then I know that my function is headed towards a particular y value. And I'm hoping that you see the pattern here. The y value that it's headed towards is 0. The same thing can be said with our second table of values. If I plugged in negative 100, you would get negative 0.01. If you plugged in negative 1,000, you would get negative 0.001. If you plugged in negative 1 million, you would get negative 0.000001. So in this particular case, my x values are getting smaller and smaller and smaller. So in this case, I'm looking at the case of when x is approaching negative infinity. So when my x's are approaching negative infinity, I notice that my function is getting closer and closer and closer to 0. So based on what we have from our table of values, let's take a look at defining our limits. So the limit as x approaches infinity for 1 over x, that's going to be 0 for us. And then the limit as x approaches negative infinity is also 1 over 0. Sorry, 1 over x is also 0. My apologies. So in conclusion, if we talk about our limit as x approaches positive and negative infinity for our function 1 over x, then we can say the following. Limit as x approaches positive and negative infinity for 1 over x is 0. Now I want to stop for a quick second and I want you to think about, you've done something like this before in advanced functions. We didn't use limits here, but you've done it before where you looked at plugging in a very small number into your rational function and then a very large number into your rational function. This here is talking about your horizontal asymptote, which for 1 over x, the horizontal asymptote is indeed at y equals to 0. So now, rather than what we were doing in advanced functions where we were just plugging in, let's say, a really large number or a really small number, we're going to be using limits to help us out. But like I said, that will come in Unit 3 when we start talking about graphing all over again. Now, in this particular case, we were able to use a table of values, but a table of values isn't necessarily going to be the best way to figure out the limit when you're dealing with x approaching infinity or x approaching negative infinity. So there's got to be a better way to figure out our limits at infinity. So let's take a look. Like I said, what if we asked a question like, what's the limit as x approaches positive infinity for x plus 1 over 2x minus 3? So in this particular case, if we're looking to evaluate our limits at positive and negative infinity, as x becomes large, or if x becomes smaller, both the numerator and the denominator are going to become large numbers, okay? So it isn't exactly obvious at the very beginning, what the limit is going to be. So what we're going to do is we're going to factor out the highest power of x in the numerator and then the highest power of x in the denominator. And that's going to help us evaluate our limits at infinity. So let's take a look. So for question A, I have the limit as x approaches infinity for x plus 1 over 2x minus 3. So right off the bat, we're going to take a look at the numerator and we're going to take a look at the denominator. And I want you to tell me, or at least to figure out, what is the highest power of x in my numerator and what's the highest power of x in my denominator. So I'm going to do the limit as x approaches infinity. Now, if I take a look at my numerator, the x with the highest power is just x. So what I'm going to do is I'm going to factor that out. So I'm going to factor it out, and I'm going to end up with 1 plus 1 over x. That's normal here, okay? That's actually going to come in handy for us later. I'm going to do the same thing with my denominator now. In my denominator, 2x is the term with the highest exponent. So what I'm going to do is I'm going to factor out that x, and then I'm going to be left with 2 minus 3 over x. Now, when we get to this particular stage, here's the important part that I want you to take a note at. Notice that I can divide both the x's, I can cancel them out. So I'm going to get rid of those first. And now let's talk about those situations where I've got those fractions there, right? 1 over x and negative 3 over x. I want you to think about what happens if I was to plug infinity there. So think of 1 over a super large number. That is headed towards 0 for us. The same thing can be said about negative 3 over x. If I plug in a really large number for x, this whole back portion also goes to 0 as well. So at the end of the day, when we think about going off to infinity, we're only left with 2 numbers left, which is 1 over 2. So the limit as x approaches positive infinity for x plus 1 over 2x minus 3 is simply 1/2. Let's take a look at example B. So in example B, I've got the limit as x approaches infinity for x squared plus 5x plus 3 divided by x minus 2. Again, we're dealing with a limit where x is approaching infinity. So what we're going to do is we're going to factor out the highest power of x from my numerator and from my denominator. So let's start off first by writing out our limit as x approaches positive infinity. And now in my numerator, if I take a look, I've got 2 terms with x, but I'm looking for the one with the highest power. In other words, the one with the highest exponent, which is x squared. So I'm going to factor out x squared from my numerator. So I'm going to have x squared, and then that's going to leave me with 1 plus 5 over x plus 3 over x squared. And then in my denominator, I'm going to look for the same thing. I'm going to look for x with the highest exponent. In this case, it's just x. So I'm going to factor out that x now. And then I'm left with 1 minus 2 over x. Now in this particular case, I notice that I can cancel something out. So I can cancel x squared and x. So I'm only left with x there. And then I'm going to take a note at the following. Anywhere that I see a fraction, if I were to plug in infinity, 5 over infinity would go to 0 for me. Same thing with 3 over x squared. You have infinity, and then you're squaring it, which means it's a bigger number. So 3 over a super, super big number would also go to 0. And then lastly, in my denominator, negative 2 over x, if I was to plug in infinity, that would also head to 0 as well. So I only have my numbers 1 in my numerator and my denominator, and I also have x in my numerator. So if I simplify that, in this particular case, I notice that I'm going to have the limit as x approaches infinity, but I'm going to have x. So in this case, if I was to plug in quote unquote infinity, a big number, then technically I go off to infinity there. Okay, so in this particular case, the limit as x approaches positive infinity for x squared plus 5x plus 3, all divided by x minus 2, is infinity. Let's take a look at C. So if I'm taking a look at C, we're going to do exactly the same thing. So what I've got there is the limit as x approaches infinity for x squared minus 5x plus 1 divided by x cubed plus x plus 7. Again, we're going to notice what's the highest power that we have for x in my numerator and my denominator. So I'm going to start off with the limit as x approaches infinity. And in my numerator, x squared is the highest power of x. So I'm going to factor out the x squared, and then I'm going to be left with 1 minus 5 over x plus 1 over x squared. In my denominator, the highest power of x is x cubed. So I'm going to factor out x cubed from my denominator, and then I'm going to be left with 1 plus 1 over x squared plus 7 over x cubed. So right away, I notice that I can cancel some things out. The x squared and the x cubed reduce down to 1 over x for me. And then anything that I see that is a fraction, because I'm having it over infinity. So for example, negative 5 over infinity, that's going to go to 0. 1 over infinity square, also going to 0. 1 over infinity square again, going to 0. And then 7 over x cubed definitely is going to be going to 0. So once I've done that, technically, the limit that I'm going to take a look at is the following. The limit as x approaches positive infinity, I'm left with 1 over x. In this particular case, now I want you to think about it. If I'm plugging in a really large number into this particular function, 1 over a really large number means that my limit is headed to equal to 0. Alrighties. Let's take a look at the last example, which is the limit as x approaches negative infinity for negative x cubed plus 5x plus 2. Now you might be looking at this and going, well, miss, this isn't a rational function. So how am I supposed to do this? Technically, you can turn almost any function into a rational function by making it over 1. So I'm going to do exactly that for you. So now what I have is the limit as x approaches negative infinity of negative x cubed plus 5x plus 2 all over 1. So we're going to go through the same process again. We are going to look at my numerator, and I'm going to factor out the highest power of x. In this particular case, I'm going to factor out x cubed. So if I do that, I'm going to be left with x cubed, and then I'm going to be left with negative 1 plus 5 over x squared plus 2 over x cubed. Now in my denominator, you can't factor anything out, so that's just going to stay as 1. All right, so now if I go at it and I take a look, 5 over x squared is going to head to 0. 2 over x cubed is also going to head to 0. Even though we're going to negative infinity, in the long run, 5 over negative infinity squared is going to reach 0. Same thing with 2 over negative infinity all cubed. It's still going to head towards 0. So that's why we can do that. And what we're left with, and this is the part you're going to have to be careful about, I'm going to be left with the limit as x approaches negative infinity. Now, I had x cubed left, and then I also have my numbers. I have negative 1 over 1 left, which is really technically times negative 1. So the real function that I'm now taking a look at before I evaluate is negative x cubed. So let's think about this now. If I was to plug in negative infinity into x cubed, so think of a really large negative number. If you were to cube it, you would still get a negative number, right? But then because we're multiplying it by a negative sign outside, that makes it positive infinity instead. So that's going to become positive infinity instead. So you got to be careful with the signs in this particular example. But there we go. This is how we evaluate limits as x approaches either positive infinity or negative infinity. Now, just as a quick thing in terms of the note, okay, when you're evaluating, so I'm going to write it at the bottom here, when you are evaluating polynomials, oops, Miss Lynn forgot how to spell evaluate. When you are evaluating polynomials, when x approaches positive or negative infinity, you can actually just look at the leading coefficient to help you out, or the leading term, okay? So when you're looking at when x is approaching positive or negative infinity, only look at the term with the highest exponent to help you out. So technically speaking, for example D, I didn't have to do all of that work. I could have just focused on negative x cubed and then thought about if I plugged in a negative small number, let's say negative 1,000, negative 10,000, what would my final answer be? Okay, so you could have done it that way instead, but I thought I would show you if I turned it into a rational function, is it possible as well?